In this video, I'm going to talk about different conventions for drawing organic molecules. So we should probably start off by establishing what makes a molecule be an organic molecule. And the rudimentary definition would be any molecule that contains carbon and isn't a rock. So not the carbonates, not the bicarbonates, not carbon dioxide, but almost everything else that contains carbon. And the reason for this is that historically, organic chemistry was the study of molecules from living organisms, and proteins and fats and carbohydrates and all of the other molecules inside of us that aren't water, or at least most of the other molecules inside us that aren't water, contain carbon atoms. But after a while, chemists branched out and expanded and started making molecules that were very similar to molecules that came from living organisms. And it didn't make any sense to discuss those molecules separately because they behaved in the same sorts of ways, they followed the same sorts of rules, and so organic chemistry expanded to encompass these other molecules that were similar in structure to molecules that came from living organisms. And at some point, the definition just broadened completely to encompass all carbon-containing compounds that aren't rocks. On the next couple of pages, I talk about different careers relating to organic chemistry, and maybe some of that information will explain to you why it is that your major has decided that you need to take chemistry and organic chemistry if you don't happen to be a chemistry or biochemistry major. But I'm not a big fan of reading slides, so I'll let you read those on your own time. And I'm going to jump ahead to the page where we start actually drawing organic molecules. So things that are important to know. Carbon atoms, if they're neutral, are going to tend to have 4 bonds. That might be 4 single bonds, it might be a double bond and 2 single bonds, it might be 2 double bonds or a triple bond and a single bond, but the number of bonds is going to add up to 4 unless the carbon has a charge on it. That means that carbon atoms can be tetrahedral. That's what happens when they have 4 single bonds. So we might have a molecule of methane, for example, and it would have a tetrahedral geometry, looks like this. We might have molecules that are trigonoplanar. For example, formaldehyde has a double bond and 2 single bonds, and that makes it have a trigonoplanar geometry at the carbon atom. Or we might have linear carbon atoms, as we do in ethine, more commonly referred to as acetylene gas. One thing that you will note is that none of these molecules have 90-degree angles. It is very common for some introductory textbooks to decide that it will be easier for you to see all the atoms if they draw things in a 90-degree crisscross form like this. This is the last time you are ever going to see me draw a molecule that way, because that's not what they look like, and it gives you a very false impression as to the three-dimensional shape, and that's a big problem when we start talking about reactions, some of which rely on the shape of the atom, some of which will work on a tetrahedral carbon atom but won't work on a trigonoplanar atom, for example. In some reactions, you need to have the electron pair donor approach a carbon atom at 180 degrees to the group it's kicking out, and that doesn't work if you don't understand that there's no 90-degree angles. And so for that reason, that's the last time you're going to see me draw 90s, unless I'm drawing cyclobutane, which is a 4-atom ring and necessarily forces 90-degree angles. But instead, I'm going to draw my molecules zigzaggy, because the zigzaggy shows the true shape of the carbon atom, if it happens to be tetrahedral. So in many of your previous courses, you've gotten away with just writing molecular formulas. You could just write CH4, and that was fine because there's only one way to connect the atoms in CH4. It has to be a carbon in the middle with 4 hydrogen atoms around it. There's no other way to do that. But as soon as we get into larger organic molecules, there's going to be more than one way to connect the atoms together. Take something as simple as C2H6O. Well, what is C2H6O? Do we have two carbon atoms followed by an oxygen atom? Or do we have two carbon atoms with an oxygen atom in the middle? Because as it turns out, these are very different molecules with very different properties. And of course, I need to attach my hydrogens. And you can see I'm using the wedge and dash notation to indicate tetrahedral geometry. The wedge shows the hydrogen atom pointing toward me, and the dashed wedge, which is supposed to be getting bigger as I work my way away from myself, away from the atom I started at, is showing atoms that are pointing away from me behind the plane of the page. And so these are my two options for C2H6O. Very different. The one on the left is an alcohol. It can hydrogen bond. It's a liquid at room temperature. The one on the right is an ether. It can't hydrogen bond with itself, although the oxygen could hydrogen bond with hydrogen atoms in other molecules. And it has a much lower boiling point. Very different properties, function very differently, but they're both C2H6O. And in organic chemistry, we care. That said, this is very big and clunky, and there will be cases in which it's necessary to draw the molecule out in full. And when you're starting off, it's extremely helpful oftentimes to convert other notations into looking at the molecule in full, looking at this structural formula. But eventually, you're going to get to the point where you're very good at looking at molecules and understanding what you're reading, and you'd like some shorter ways to write them. So one way that we can condense this structure while still maintaining all of the information about which atoms are attached to which is to condense it down. And so if I wanted to write the molecule on the left in condensed notation, then what I would do is I would say, well, there's a carbon on the end and it has 3 hydrogens attached. And then there's another carbon and it has 2 hydrogens attached. And then there's an oxygen and it has 1 hydrogen attached. And so this is the condensed structural formula for the full molecule of ethanol that I drew at the top left of the slide. To do the molecule on the right, I would say that I have a carbon atom with 3 hydrogens attached, and then I have an oxygen atom, and then I have another carbon atom with 3 hydrogens attached. And this is the condensed way of writing the ether at the top right of the page. You can see that if you were writing out a paragraph of text, it would be much easier to insert the condensed structural formula into your sentence than it would be the full expanded structural formula. In all honesty, though, most of the time we're not going to be inserting our structures into paragraphs of text. We're going to be drawing pictures, and we're going to be using arrows to show electrons moving around, and we're going to be looking at 3-dimensional shapes. So we oftentimes like to preserve that information. But we will find as we draw bigger and bigger molecules that if we insist on drawing every single hydrogen atom, the picture gets very cluttered very quickly. And so that has led to the development of something called a line bond structure. And what we do in a line bond structure is we take, and I'm not drawing a line bond structure right now, I'm redrawing my ethanol molecule. What we do is we take the full shape of the molecule and effectively we replace each carbon atom with a dot, and then we connect the dots, and in this case the oxygen stays because it's not a carbon atom, and we erase all of the hydrogen atoms that were attached to carbons, with the exception of the hydrogen in an aldehyde, which we'll talk about later. And oftentimes we will also take bonds like the OH bond that you see there and condense them down so that it looks like this. And I'm going to ask that you continue to leave your lone pairs on your heteroatoms, your atoms that are not carbon or hydrogen, because that's going to help you out in the long run. When we start talking about reactions, you're going to struggle if you don't see those lone pairs. So get in the habit of drawing the lone pairs. And so that's what the line bond structure looks like for ethanol, the molecule that was on the left on the previous page. And if we do the same thing for the ether molecule that was on the top right-hand side of the page, again, we replace each of our carbon atoms with a dot, and we connect the dots, leaving all of our heteroatoms still showing, and the lone pairs on them. And we erase all of the hydrogen atoms connected to carbon atoms, again, except for the H of an aldehyde. And that gives us the line bond structure for our ether molecule. It is very important to understand that while you can mix and match to a certain degree, if you're not explicitly told draw and line bond, it's not inherently wrong to do something like this if it's clearer to you. That's a partially condensed type formula. That's not wrong. But what is wrong is drawing the C's if you don't have the H attached. This is wrong because drawing the carbon explicitly and not drawing the hydrogens suggests that this carbon has no hydrogens attached, suggests that this is a really funky, unusual molecule, and we need to pay attention to those carbon atoms because they've got no hydrogens on them. So the second you draw a carbon atom, you must draw the hydrogen atoms attached to it as well. And so I will go back to my nice line bond structure, which is behaving and obeying the rules. And so now I'm giving you a couple of molecules to practice drawing in each of the three formats. And I would suggest that you pause the video, give it a try, and then when you're ready, unpause, and I'll work through them. So I'm going to start by drawing the structural formulas for the compounds where that wasn't provided. So if we look at the second row of the table, we can see that we've been given the condensed structural formula for allyl chloride. And in this case, we have a carbon atom with a double bond to another carbon atom, and then a single bond to another carbon atom, and then a single bond to a chlorine atom, which we know should have 3 lone pairs. And the carbon at the left has 2 hydrogens attached. It's got 3 electron groups, so we should be showing trigonal planar electron group geometry. Please show roughly reasonable bond angles in your structures. We're not going to pull out a protractor, but don't give us 90-degree angles where they're not. The carbon in the middle has 1 hydrogen attached, and this carbon over here with the chlorine on it has 2 hydrogens attached, so it has roughly tetrahedral geometry. For the bottom row of the table, we can see that we have a line bond structure, and every dot or every bend in the chain has 1 carbon. So we're looking at a 5-carbon chain here. The middle carbon atom has a double bond to oxygen. And then each of the other carbon atoms has enough hydrogen atoms such that it obeys the octet rule. And so essentially add enough hydrogens to give every carbon atom 4 bonds. So in this case, we're going to have 3 hydrogens attached to the carbon on the end, and same for the other end. And then we're going to have 2 hydrogen atoms attached to each of our carbons in the middle. We can see that that was rather large to draw. And so if we want to condense it down a little bit, but not go quite as far as line bond, we can do that. We can say that there was a carbon on the end with 3 hydrogens attached, and then a carbon with 2 hydrogens attached, and then a carbon with a double bond to an oxygen. And if you're hand drawing, you can do this. And I'll show you what to do if you're not in a minute. Then we have another carbon with 2 hydrogens, and then another carbon with 3 hydrogens. If you were actually writing this in text and needed everything to be in one line, you would say I have a CH3 and then a CH2, and then my carbon has an O attached off the chain, which is what those brackets mean, is O off the chain. and then I have a CH2, and then I have a CH3. You're not going to be able to write a condensed structural formula for the top structure that fits all in one line. In some really ancient old-fashioned papers, you'll see people try, and they have these fun, crazy lines across the top. Here, I'm going to acknowledge that I am going to have to show my hexagon. There's not much I can do about that. But instead of expanding out every single CH bond, I'm instead just going to note how many hydrogens are attached to each of my carbons. And you can see why we don't tend to use condensed structural formulas a whole lot for rings, because they don't really help that much. On the other hand, drawing it line bond is helpful. So if I put a dot where every carbon atom was in my hexagon, and then I connect those dots with the right number of lines to show the bond. So those were all single bonds, but the two carbon atoms on the right over here have a double bond. And then I add all of my heteroatoms, so oxygens, nitrogens, sulfurs, halogens, all of those, and any hydrogens that might be attached to those. In this case, there aren't any. And then for my last line bond structure, it's the same thing. I have 1, 2, 3 carbon atoms. These two are connected by a double bond. These two are connected by a single bond. And I have 1 chlorine